So far in biology class, we started talking about different molecules that help you live. Now, this unit is going to be about creating chemical reactions of the food that you eat so that you can live. So your first main question here, which is going to be why do we need to eat, which everyone loves to do, is so that you can gain energy. Without energy, there would be nothing like this at all. So the next question is, where does the energy come from when you eat? So if you recall what some of our macromolecules look like, for example, this particular one, which is a lipid. As you can see, there are tons of chemical bonds, these little lines in between each carbon atom, and as your body will consume this food, your digestive system will cause these little tiny chemical bonds to break, and as every individual bond breaks, more and more energy is released. So that's why the more food that you eat, the more energy is available to you. A chemical reaction is a process of changing one set of chemicals into another set of chemicals. This happens all around us, every day, all day, constantly, and it's probably something you don't even realize. If you take an ordinary match, the color of the tip of the match before you light it is red because it's made of one set of chemicals. After you light the match, you'll see that the color of the top of the match changes to like a charred black color because it's now a new set of chemicals. The next slide will show you a video of that example. Now another example of a chemical reaction is when you eat food. The food that you consume will go inside of your body from chewing and digestion inside of your stomach and your intestines. You will use certain types of chemicals to break the chemical bonds inside those molecules. For example, the molecules that hold the sugars together in a carbohydrate will be slowly broken down by your digestive system, and every time they are broken down, certain amounts of energy is being released. Now here is another example of a type of chemical reaction when you take baking soda, which is this molecule right here, mixed with vinegar, which is this one, and when they combine, you're going to take the sodium bicarbonate, which is which is baking soda, and it's when it's mixed with vinegar, when you're done, you're going to end up with just pure water and carbon dioxide. So as you can see, you start out with one type of molecule, it chemically changes into another set. Here's a video to show you. Now, when chemical reactions occur, the chemical bonds that hold these molecules together are broken. In order for this reaction to occur, there either needs to be energy put in or energy released. This slide basically says the same thing. How do energy changes affect whether a chemical reaction can occur? In order for that chemical reaction to begin, you either need to add energy or have energy released from the reaction. Again, now in order to start a chemical reaction, some chemical reactions can happen spontaneous, like the baking soda and vinegar, or sometimes chemical reactions need energy to be put in, like starting the match, in order to start the reaction. Now, just a basic vocab word that you'll need to know is called activation energy. And the simple definition of activation energy is the amount of energy you need to activate a chemical reaction. It's pretty simple. Now there are two types of chemical reactions when dealing with energy. This one right here, as you can see, is energy absorbing, where this chart here is what's called energy releasing. Just like this little guy here who's pushing up this giant snowball up a hill, if you don't put enough energy into a type of reaction, just kind of like if this guy doesn't push this snowball all the way up to the top, what do you think is going to happen if he doesn't put enough energy? The snowball is going to simply run him back over. So that's kind of like a chemical reaction. If you don't have enough activation energy or enough energy to start the chemical reaction, the reaction simply is not going to occur. Now, this is a chart of a chemical reaction which is called exergonic, which is energy releasing. Now, if you look at the first half of this chart, so just try to imagine that you have this line separating the two sides. This side on the left is before the reaction, and on the right side of the line, this is after. The top part here, this is where the actual chemical reaction will occur. So what you see right here, from this side to here, what I'm drawing in red, this measurement in red is the amount of energy that needs to go into the reaction in order to hit this top point in order to cause the chemical reaction. And then afterwards, since we're now on the right side of the line, this is the amount of energy that's coming out. As you can see, this side right here, this is extra amounts of energy because this whole top half is equal. That's why they're the same amount of sides. Where this bottom half here is showing extra amounts of energy at the end of the reaction. Hence, this is the amount of energy that's releasing. And the other word for that is what's called exergonic. Now, in reverse, this is now what's called endergonic. As you can see right here, this is endergonic. Endergonic is instead energy absorbing. So if you look at your chart here, as you can see, this, as you hit up to, remember, at the peaks, this is where the chemical reaction occurs. This black line is a chemical reaction without assistance of an enzyme, and we'll get into enzymes in a second. Now, in order to start this chemical reaction without an enzyme, you would need to have this great amounts of energy in order to start it. It's kind of like adding fire, because fire, if you don't know, is energy. So you would need to add enough heat in order to cause this chemical reaction. Yet at the end, you're only getting back less amounts of energy, because this side right here is more amounts of energy. This is extra amounts of energy and there's none right here. So this is showing less amounts of energy. Therefore, the excess energy that came from right here is being absorbed within the reaction. Now, in order to get this reaction to speed up, sometimes you can lower, that's what you have this red line here, you can lower the amount of energy required to start the chemical reaction, which is what's called lowering your activation energy, because your activation energy is the amount of energy you need to start the chemical reaction. Therefore, this is an example of an enzyme, and this is how we speed up chemical reactions. Now, I understand this is confusing, so I hope that you are writing down some questions at this point, so afterwards we can go over that. So to review, how does an enzyme cause a substrate, which is the end result of a chemical reaction, to change? And it's by lowering the rate of activation or lowering the activation energy, which means it's requiring less energy to make the chemical reaction start, so therefore the reaction will start faster. Now, enzymes, which cause chemical reactions to go faster, is required inside of especially complex organisms like ourselves. Since we are constantly thinking, moving, breathing, heart beating, we're doing 1,000 things at once at all times, even when we're sleeping, we need enzymes in order to speed up the chemical reactions in our body so that we can process enough energy to live. So we have hundreds of different kinds of enzymes in our body that allow for us to break down more food faster and gain more energy quicker. Here is a random fun video that has nothing to do with this, just to make this a little more fun. Now back to enzymes. Here is an enzyme, which is this bottom part right here, paired with what's called its substrate. So the substrate, which is this red part, which is the molecule before it goes through a chemical reaction, and then afterwards, as you see right here, it's called the product, about what it looks like after the chemical reaction. These are just some very simple vocab terms. As you read here, some chemical reactions that make life possible are too slow or have activation energies that are too high to make them not practical for living. So we have what's called a catalyst. This word catalyst right here means something to speed something up. As it says right here, a catalyst is a substance that speeds up the rate of a chemical reaction, and a catalyst works by lowering the amount of activation energy. Again, lowers the amount of energy needed to start the chemical reaction. Again, here are some more simple vocab terms. A reactant is an element or compound before the chemical reaction. Another vocab term is a product, which is the element or compound after the chemical reaction. So this is the chemicals that the chemical reaction produces, hence why it's called a product. So a substrate is the substance or molecule which the enzyme alters. So now this is the chemical reaction that occurs inside of your human body. So the substrate is the chemical or molecule that the enzyme is going to act upon. Now an active site is the exact location where the enzyme will connect with the substrate to cause the chemical reaction. Here is a good diagram or picture that will try to explain this a little better. As you can see right here, this is your substrate. This gray matter is the enzyme. And right here, where they're actually touching and connecting, is called the active site. As you notice, they fit together like a puzzle piece. This is what's called the lock and the key mechanism. Hence why you only have one lock that matches with one key. You'll never have one enzyme that'll work with multiple compounds. It'll always be one enzyme to one substrate. Again, here's just another picture of your enzyme, your substrate. They will connect together inside the active site. This is just a simple study tool. Any enzymes will always end in the words ASE, kind of like how sugars always end in OSE. If you remember that study tool, this is just another one where enzymes will end in ASE. Now there are some factors in this world that affect how enzymes work. There are two of them, temperature and pH, which is your scales of acids and bases. Especially with temperature in the human body, this is why getting a fever can be very dangerous. Because if your fever, which is your body temperature, goes too high, your enzymes will not work anymore, and that's why you can get even more sick, or possibly extreme high fever can eventually kill you if you're not careful. Here is some basic information that explains why certain factors affect enzymes. And to summarize is, if the pH or temperature is off, the original shape of the enzyme will change. Therefore, the enzyme will not fit with its substrate like a lock and a key, and the chemical reaction cannot occur faster.